Hello and welcome to Lecture 5 for Unit 3 of Introduction to Logic. Today we're starting a new part of the unit. We're going to be doing derivations for predicate logic, that is, derivations for this new logical system that we're learning. And just like in Unit 2, we use derivations to prove that an argument is valid. And it's really important for predicate logic that we have a method for showing that an argument is valid because unlike sentential logic, we don't have a method like truth tables for predicate logic. There is a method I could have taught you, but it's actually more complicated than derivations. So we're going to start with derivations. And the basic idea of a derivation is the same for predicate logic as it is for sentential logic. You want to break down the reasoning behind an argument into a series of steps, each of which is obviously valid. And we're going to use all the same rules that we learned for sentential logic now applied to predicate logic. The only thing to remember is that in the statement of the rules, the letters like the A, B, and the C are placeholders for any statement simple or complex. Now, we're still going to look at those same rules, but we're going to interpret them differently because now the A, like in modus ponens, if A then C, A therefore C, the A and the C are never going to be replaced by a single letter all by itself. It's always going to be plugged in by something more complicated. The simplest thing you can plug in for fancy A in the statement of modus ponens is something like FA. But they could contain other things like quantifiers or more complicated forms, but the rules all apply. So there's some derivations we can do just using the rules you already know. So let's look at this derivation. FA, first premise, A is F and something is G. Something is G, second premise, something is G if and only if B is H. Show that A is F and B is H. So we can do this using direct derivation. Nothing has changed. So we write dd for direct derivation, put in a new line. And now we can take line 1, which is an and statement, we can break it into its two halves. So we write fa, that comes from 1, ampersand out, just like it would in our previous unit. Break up line 1 again, get the other half of line 1. Something is g, and we'll write the forward z for the backward z. Something is g, again, line 1, ampersand out. Then we want to use line 2. Line 2 is a two-way arrow statement. So the two-way arrow changes to the one-way arrow. So we need, if something is g, then b is h. That comes from 2, double arrow out. Then we can do modus ponens with 5 and 6, right? So 5 says something is g, 6 says if something is g, then b is h, so we get b is h. 5 and 6, modus ponens again is called arrow out. And then we can put FA and HB together to get FA and HB from 4 and 7 ampersand in. And then we can check our derivation to see if we did it right. And we did. So it doesn't use any new rules or anything like that. All the old rules carry over. We can still do derivations with that. Let's look at the next one. So the next one, we're going to do a conditional derivation because that carries over as well. So the premise says, if either MA or NA, then everything is O. Show if A is N or NA, that everything is O. We'll do this by conditional derivation. We'll assume that A is N. New show line to show that everything is O. We'll do that by direct derivation. So the premise says if MA or NA. We can get if MA or NA from line 3 by or in, right? If you have half an or statement, you get the whole or statement. So now we have what we need to do modus ponens on 1. That gives us everything is O. 1 and 5 arrow out. So it's 1 and 5 arrow out, 5. Now we've shown that everything is O. We've shown that if NA, then everything is O. There we go. Now I want to point out something about line 2 there. So line 2, it's if NA, then everything is O. If we had everything, the quantifier at the beginning, for all x in parentheses, nx arrow ox or na arrow ox, then the quantifier will be the main operator. So the quantifiers can be operators, but they take narrow scope. So if there aren't parentheses after them, they just apply to what comes immediately after them. So the arrow is the main operator in both 1 and 2 of this particular derivation. But if the quantifier were at the beginning with parentheses right after it, the quantifier would be the main operator. So we need rules for the quantifiers, and that's what we need to talk about next. So if the universal operator is the main operator, the rule you would use for a certain rule is universal out. So we need something to use when our main statement we have as main operator is the upside down A, and we need a way of getting statements whose main operator is the upside down A. We're going to start with using one. We need the out rule for the universal operator. So I don't like the way the out rule is written in the book, and it looks even worse on my particular tablet right here, because my tablet doesn't have the fonts for the fancy letters. So the main idea behind universal out is what's true of everything is true of some particular thing. So let's look at the example down here. So this is the example. For everything, if it is human, then it is mortal. What's true of everything is true of some particular thing. So therefore, if Socrates is human, then Socrates is mortal. So we would write, for everything, if it's human, then is mortal, or all humans are mortal. For every value of x, hx arrow mx. Notice that there's parentheses after the quantifier. So the quantifier is the main operator. The arrow is inside parentheses. So we use universal out on this before we would use any other rule. So universal out on it, what we do is you take off the quantifier, you take off the for all x, and you change the x to some letter at the beginning of the alphabet, A, B, C, up through W. So we change the x here to S. We get HS arrow MS. So the informal version of universal out, look at the informal version. If you have something that starts with a quantifier for all x, and it's got some statement, the quantifier is the main operator that has an x in it, you can replace that x with a name like A, B, or C. What's true of everything is true of any particular thing. So if something is true of everything, then it's true of Socrates. So the way this is written in the book looks a little bit funny. You have for all v, it could be any variable v, then there's some that should be a fancy letter A, some statement that comes after it that has the variable v in it. And what you get is what you get when you substitute A for v. That A/v is what you get when you substitute A for v in fancy A. So the way that's written is kind of confusing. It's not really a problem if you don't entirely understand it. But the important thing is that you know how to use this rule when it comes up. So let's do some examples. For every value of x, if fx, then gx. For every value of x, if gx, then hx. D is f. Show that d is h. So we're going to do this by direct derivation. We want to use line 1. So the main operator of line 1 is the universal quantifier, the upside down A. It's not the arrow. The arrow is inside parentheses. So we can't do modus ponens or modus tollens on 1 the way it's written. What we can do is we say instantiate the variable. We can take off the for all x. We can replace the letter x with any name we want. So we can replace it with A, we can replace it with B, we can replace it with C. It's true for everything, so it's true for any particular thing. The thing we care about, though, is D, because that's what the third premise is about. So if we take off the for all x in 1, replace the x's with d's, we get FD arrow GD. That comes from line 1, universal out. So we can write AO for universal out. Now we can do modus ponens on 5 because we have FD and we get GD. 3 and 5 arrow out, because now in 5 the arrow is the main operator, so we can do arrow out on that. And we want to do something similar with line 2. We want to take off the for all x at the beginning, change the x to some name. And again, we want to change it to D because D is what we care about. So we change the x that comes after the G to a D, we change the x that comes after the H to a D. We have to change all the x's to the same letter. All right, so that's 2 universal out. And now we can do modus ponens with 6 and 7 and get HD. That's what we were trying to show, so we can box our box and cancel, and we can check our derivation. There we go. So all universal out is you have some universal statement, a statement about everything, and you change that statement about everything to a statement about some particular thing. That's universal out. Right? sometimes it makes sense to universal out more than once in the same statement. So we'll see that on the same statement. We'll see that in this one. So the first premise says everything is both f and g. So A is both f and g, B is both f and g, C is both f and g. The second premise says if A is f and B is g, then everything is h. We're going to show that C is h. And again, we can show this by direct derivation. So we're going to start with line 1, and we can take off the for all x. We can change that x to whatever we want. We can change it to A, we can change it to B, we can change it to C. I'm going to start by changing it to A. And we have to change both x's to the same letter. So I have to change both the x that comes after the f and the x that comes after the g to A when we do universal out. Because we care about getting that A is f, so we just got that A is f, or we can on the next line by breaking up line 4. But we also want to get that B is G. So I'm going to go back to line 1 and get that B is both F and G, right? Because it's true about everything. It's true of both A and B. So we can do universal out on the same line more than once. And then we get the B is G from 6, breaking up 6. Now we can't change one of the x's to A and one of the x's to B on the same universal out. You've got to use the same letter every time you change the variable to a letter. But now we have FA in one line and BA in another line, GB in another line. We can put them together, FA and GB, from 5 and 7, ampersand in. Now we have what we need to do most ponens on 2. So we get everything as H. So that's 2 and 8, arrow out. And it doesn't matter that the universal for 9 uses a y rather than x. It's the same rule. We can change the y to whatever we want. Now we're trying to show HC, so we're going to change that y to a C. We take off the for all y, change all the y's to the same letter. We'll change them to C, and we get that. Very good. Here we'll do an indirect derivation, and we'll show that not everything is f by assuming that everything is f and getting a contradiction from that. So the first premise, either not fa or something is g. It's not true that something is g. Show that it's not true that everything is f. We're going to do this by indirect derivation. The negation there is the main operator in the show line, so we're going to assume that everything is f and show a contradiction from that. And again, you show splat. You're doing an indirect derivation. You assume the opposite of what you're trying to prove, then you try to prove a contradiction. That's just review from Unit 2. Okay. So notice that line 2 is the negation of one of the two sides of line 1. So line 1 says that either not FA or something is G, but 2 says it's not true that something is G, so we get not FA. From 1 and 2 wedge out. But line 4 says everything is everything is F, so we get that A is F. Right? Take off the for all x and 4, change that x to whatever letter we want. We'll change it to an A. And now we have two lines that contradict each other. We can write splat. That's 6 and 7, splat in. So we've shown splat. We've shown it's not true that everything is F. When you have multiple quantifiers, you just take them one at a time. So look at the first premise of this one. For all x and for all y, rxy. So the main operator there is the for all x. The for all y is not the main operator since it's on the inside. So when you do this, you just take the for all x first. We're going to do this one by direct derivation. So everything respects everything. That's basically what line 1 says. Everything that respects itself is friendly. Show that A is friendly and that B respects A. So line 1 is about everything. We can make it about A. We just take off the one quantifier at a time. So we take off the for all x, leave the for all y there. You can change the x's. You don't change the y's. You just change the variable that goes to the quantifier you're taking off. So we can replace that x with an A. We could also replace it with a B. Again, sometimes it makes sense to universal out more than once. So I'm going to do it to A and I'm going to do it to B. So line 1, if I take out the for all x, change the x's to b's, I get this. So line 4 says A respects everyone. Line 5 says B respects everyone. Those both come from line 1. Universal out on 4 gives me that A respects A, right? I can change that Y to whatever I want. I can change it to an A, I can change it to a B. I'm going to change the Y in 5 to a as well, get RBA. That's one of the two things I need to get, right? And then line 2 is a universal statement too. So I can universal out on 2. I could change those X's to A's. I can change them to B's. Now I want to change them to A's since I'm trying to get FA, right? If I get RAA, which I already have, I can get FA if I change the X's in 2 to A's. So I'll change the X's in 2 to A's, get RAA, arrow FA, right? 2 universal out. And now I can do most ponens on 6 and 8 and get FA. Now I have the two things I need to get line 3. I get FA and RBA. So that's 7 and 9, ampersand in. Very good. So that's universal out. That's a way of using a universal statement. If you have a line whose main operator is a universal statement, you want to think about doing universal out on it. You take off the quantifier in the variable, you replace all the occurrences of that variable with some name. It can be any name you want. You can do it more than once to multiple names if you need to. That's universal out. So really in this unit we need 4 rules. We need a universal out way, we need a way of getting a universal statement, we use a way of using an existential statement, that is the backward Z statements, and a way of getting existential statements. So the next rule we're going to talk about is the way of getting existential statements, that is a backward Z statement. It's called existential in. And the reason we're taking it next rather than existential out is that it's simpler, it's an easier rule than existential out is. So we're going to start with existential in. And it's kind of the reverse of universal out. So universal out says what's true of everything is true of any particular thing. Existential in says that what's true of some particular thing is true of at least one thing. So if you have a statement that, look at the informal version. If you have a statement that has a name like A in it, you can get there is an X, blah, 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 where you replace the A with the letter X, changing one or more occurrences of that name to the variable and adding the existential quantifier at the beginning. So let's look at the example. The Bandersnatch is frumious, therefore something is frumious. What's true of B is true of at least one thing. So if at FB, then there is an XFX. So what you do is you take some statement that has a name in it, you replace the name in at least one spot with a variable, and put an existential quantifier at the beginning of the statement applied to the entire statement. So again, the way the official version of it looks is kind of confusing, but so long as you understand how the rule actually works, you shouldn't have any trouble. So let's try an example of that. So let's look at this statement. For all X, X is either F or G, B is not F, so something is G, right? So we'll do this by direct derivation again. So we're trying to get an existential statement. If I can get GB, I can get something is G. That's existential in. But to get GB, I first have to make line 1 about B. So again, I'm going to do universal out on 1, change those X's to B's, take off the quantifier at the beginning, and I get if everything is either B, F or G, then B is either F or G. But I have at line 2 that B is not F, so I get that B is G. That's 2 and 4 wedge out, right? If either FB or GB, but not FB, we get GB. So here's where we do existential in. We've got that B is G. If B is G, something is G. So we put the quantifier at the beginning, I replace that B with an X, and I get there is an X, GX. That's 5 existential in. Very good. Let's do another one. We'll do this by direct derivation as well. For all X, Fx if and only if Gx, we can make that about B. Fb if and only if Gb. We have Fb and we're trying to get Gb, so I'm going to make line 4 go from the left to the right. Right, that's 4, double arrow out. So then we get GB from line 2. Line 2 and 5, arrow out. We have FB, we get GB. Now we're trying to get something that's either G or H. So the existential in is going to put the existential as it's going to replace, it doesn't change anything else about the statement. So what we need to get is first we need to get GB or HB. We can get that from GB by or in. So by wedge in on 6, we get GB or HB. And then when we do existential in, I can replace one of the x's, like I could get GX or HB, or I could replace both of them, or I could just replace the second one. Any of those are allowed, but we're trying to get the show line. So I'm going to replace both the b's with the same variable x. All right, so that's existential in on 7. Okay? Sometimes it makes sense not to change every occurrence of the name to the variable, and that's different from universal out. When you do universal out, you've got to change all the variables to the name. But when you're going from the names to the variables, you don't have to replace all the names with the variables, and sometimes it makes sense not to. So let's look at this one. For all x, txx, arrow sx. Sometimes I like to make up what that means. For every x, if x tickles itself, then x is silly. Not se. Emily is not silly. Show that there is an x and a y where x does not tickle y. There's something that does not tickle something. So we'll do this by direct derivation as well. So we need to make one about E, about Emily. If Emily tickles herself, then Emily is silly. So we're doing universal out on 1. Now we can do modus tollens on 2 and 4, right? If TE, then SE, but not SE, so we get not TEE. So 2 and 4, arrow out. Now if Emily does not tickle Emily, then there is a Y where it's not true that Emily tickles Y. Now the reason I'm doing the Y first is I'm trying to work my way up to that show line. The show line has the backwards EY inside, right? And I don't have to change both the E's to Y's. I can just change one of them. I'm just going to change that second one because I'm trying to make that into Y, not trying to make the first one into Y. Next step is I'm going to do existential in again, right? So if Emily doesn't tickle herself, line 5, there is something that Emily doesn't tickle. 5 existential in. Then we can do the next one. We can do existential in again since there's still an E in there. There is a Y, not TXY. That's 6 existential in. Very good. All right, so we're going to do one more. This one we're going to do by conditional derivation. Since the main operator of the show line is a conditional, we're going to assume FA, then show this existential. So we're going to get this existential by existential in. That's a direct derivation rule, so we'll get it by direct derivation. All right, so we have something about A at line 4. We want to make line 1 and line 2 about A. If FA, then GA. I'll go ahead and do the same thing to line 2. If FA, then not HAA. We change all those x's to a's when we do universal out. Now I can do modus ponens on line 6. I have FA. If FA, then GA, so I get GA. 4 and 6 modus ponens. Now I can do another modus ponens on line 7. If FA, then not HAA. We get not HAA from 4 and 7 modus ponens. And what am I trying to get? I'm trying to get there is something that's G that does not bear H to A. So A is G. Put 8 and 9 together to get GA and not HAA, right? Because that's the something that's A that does not bear H to A, right? So 8 and 9 ampersand in. Now we've got a statement in line 10 that has 3 A's in it. When we do existential in, we can change as many or as few of those A's to X's as we want. A is G and A does not bear H to A. So there is something that's G and not HXA. So the reason I'm changing the first two A's to X's and leaving the third one there is because I'm trying to match the show line at line 5. But this comes from 10 existential in. All right. So universal out and existential in, that gives you enough to do exercises 8A, 8B, and the first set of credit exercises for the derivations, so exercise 3.2. That's it for lecture 5. I'll see you in the next one.